we talked about part of this on Friday. And so we use the function w to relate those two. So we said d equals w of t. D equals w parentheses t is the function notation for that. So where we left off was in the middle of question 2, looking at, if I can pull this back out here. We said the distance traveled by the car in the first 9 seconds that it was moving. If I want to know how far it traveled between one point in time and a second point in time, that's one of our relationships we started talking about the second day of class. Just final minus initial tells us the variation or the amount of change in one certain quantity. In this case, over a period of time that lasted from time 2 seconds to time 9 seconds. Or no, the first 9 seconds. There, 2 to 9 was down here. First 9 seconds was, ooh, let me not do that. Get this back to normal size writing. All right, between time 0 and 9, and we discussed there's a couple different ways we could write this, but on the interval time 0 through time 9, the final time 9 and the initial time 0 would correspond to positions w of 9 and w of 0. So if I wanted to write the change in distance, final minus initial, the positions would be w of 9 minus w of 0. And like we said, w of 0, since this is distance since the car started moving, w of 0, at 0 seconds since the car started moving, the distance traveled would be 0. But just because we know that fact, would this be the same as w of 9? Right. So not all the time is this something of 0 always equal to 0. In this case it is, though, because of the description. Since something started moving, it's gone 0 after 0 amount of time, whatever the units are. So let's see, the change in the distance traveled or the variation in distance as the car moves from time 2 to time 9 similarly was just w of 9 minus w of 2. So the next ones were the ones that were a little bit more challenging. So w of 2 probably would not be 0, nor would w of 9. So we'll just have to leave that as this. Let me ask this question. W of 9 minus w of 2, is that the same as w of 7? No, what would w of 7 mean? W of 7 doesn't mean anything about time 2 and time 9. It means, yeah, this would be how far it traveled in the first 7 seconds, or alternatively, it's distance traveled by 7 seconds into the after it moved. Just, yeah, this is not the same as that. This is in the first 7 seconds. So it's not the same as this. You can't subtract the 9 and the 2 there and get something, you have a different meaning. So this w of 2 means that dependent quantity, the distance that the car has traveled after moving for 2 seconds, the distance that the car has traveled after moving for 9 seconds. Now, if the car was traveling at a constant rate, those could be equal. Do you think it's likely that a race car is going to travel at the exact same speed from the time it starts moving to 9 seconds later? No, it's probably accelerating, right? It starts out not moving, and then they go faster as fast as they possibly can. They're trying to win a race. So it goes from 0 to really fast, and probably before it gets to 9 seconds, they get to their top speed. But in any case, sorry, that's distance. And for 7 seconds, these could potentially be equal, but they aren't guaranteed to be by anything in this problem. All right, so let's talk about C then. C asks you to express the car's change in distance traveled during the second 4-second interval after beginning to move. So what interval would that be? What interval of t values are we talking about there? Yeah, 4 to 8, right. The first 4-second interval would be 0 to 4. The next one would be 4 to 8. So I don't have to jump to 5 or anything. There's time between 4 and 5. Just thinking about the x-axis continuing forward from 0, or the t-axis, 0 to 4 is the first 4-second interval. Going forward from there 4 more units takes us to 8. So yeah, we're talking about the interval 4 through 8 on the t-axis. So if I want to know the distance traveled during that time interval, right, I can, yeah, as soon as I know what that interval is, what are the beginning and ending independent variable values, I can write the change. The final distance, so the final dependent value is W of 8. And then the initial dependent value, W of 4. All right, that's not bad. Now, make this one step weirder. The change in the distance traveled over a 7-second time interval that begins at a general time t equal to x. So what interval are we talking about here? X through x plus 7, right. It's not x through 7, it's x through something that's 7 larger than x, 7 more than x. So whatever x is, if x was 3, this would be 3 to 10. If x was 19, this would be 19 to 26. But for a general x, this represents a 7-second time interval that begins at x and ends 7 seconds later. So distance traveled, again, we could do it the same way. So if you notice, like the problems are a little bit different from one another, but this to find a change in distance or how much the distance varies over a time interval, if you can describe that interval, then all you have to do is that y final minus y initial, where the y value is described instead of using the letter y, it's described with function notation. So we've got W of x plus 7, right, minus W of x. Is this equal to W of 7? No, still not equal to that. Yeah, you can't subtract the independent variable values and just assume that it's the same, because if I were to write W of 7, again, that would mean the distance traveled in the first 7 seconds, which may or may not be equal to the distance traveled in other sets of 7 seconds. But W of 7 specifically means this, regardless of whether the value of it's equal to some other quantity we compute later. So, any questions on this number 2? Keep in mind, you don't have to compute any of these. We just wanted to be able to express the distance traveled. We don't have a formula for this. We don't know how fast the car was going. We don't know if it started going a constant speed at some point in time. We don't know any of that. But we know that these symbols represent the things that we need to combine in order to compute, in order to express the quantities that are described. Changes in distance or a variation in distance. All right. So number 3, we had somebody else wrote expressions. And our job was to try to explain what they could possibly mean. So using stuff about the car, not just W's and A's and H's, X's, what might this 2 times W of A mean? Okay, double something. So double from the times 2. So I could think double, let's see, W of A. What is W of A again? That would, distance traveled. So double the distance traveled or 2 times the distance traveled. Yeah, so what is this? W of A, right, is the distance traveled after A seconds, or how far the car traveled in the first A seconds, because we said those were the same. So the distance, double the distance traveled in A seconds. I'm just putting quotes around that because that otherwise looks, in a seconds, looks like strange English. So double the distance traveled in A seconds. So however many A is, if it was 2 times W of 9, it'd be twice the distance traveled in 9 seconds, or double that distance traveled in 9 seconds. So the units on this would be the units of distance that we were talking about for this problem, which, what were those, by the way? Do we have units for that? Feet. So this would be some number of feet the number of feet traveled times 2 during those 8 seconds. What about W of C minus W of 8?
The distance is traveled over the time interval starting at A and ending at C.
Right. Yeah, this looks like the expressions we were writing in number 2. So this would be a distance traveled or a change in the number of feet traveled or a variation in the number of feet traveled between, let's see, which one was, again, you said it, which was the initial end of the time interval? 8, yeah, 8's the beginning and C's the ending. So this would be, I could say the number of feet traveled or just the distance traveled. We're measuring it in feet. During that interval, time interval, so this is a number of seconds, something that starts at 8 seconds and ends at mystery number C seconds. So the distance traveled during that would be a distance in feet again. And I don't know how many feet that is, but it's the feet that were traveled during this specific time interval. Now, this next one kind of looks strange, but suppose this is a math statement that makes sense of some sort or another. W of 7.5 minus 9.
The change in distance traveled in 7.5 seconds from the original 9 feet.
Okay, so yeah, if these are supposed to make sense, then this 9 would have, this W of 7.5 I know is definitely feet. If I'm going to subtract something from a number of feet and have it make any sense at all, I hope that it's going to be another number of feet. Like, this is some distance traveled in the first 7.5 seconds, and then 9 feet less than that, or how far that distance is from 9 feet past the starting line. This could be W of something or another that happens to be equal to 9, and I could subtract those and find that change in distance traveled. There's lots of ways you could describe this, but in order for this to make any sense as a why on earth would I subtract this, they should probably be the same types of things, so feet minus feet. I wouldn't want to have like 9 degrees less than the distance traveled something. That you could write that, but it wouldn't, assuming that these are sensible computations to do, it would not be 9 degrees. It'd be 9 feet that we could subtract from this, which is a number of feet. So, and you said something like the change in distance between 9 feet and where you were at 7.5 seconds. So the distance traveled,
In 7.5 seconds.
yeah,
from the original 9 feet.
right. Okay, so the distance traveled beyond 9 feet during the first 7.5 seconds. So if I figured out how far I traveled in the first 7.5 seconds, subtract 9 from that, that would be 9 feet that I'm subtracting from whatever distance that is. So it tells me, like, if there's a 9-foot line past the pit wherever the car was leaving from, there's not usually a line there, but it'd be how far I traveled past that other line that was 9 feet away from where I started. All right, so let's see. D looks more familiar. And E, those kind of look like things that we did in number 2. It's the subtracting 2W of somethings. So maybe by now we could say, oh, that's a change in the distance or a variation in the distance between 2 points in time or over an interval of some sort or another. If I wanted just to describe what interval this corresponds to, where does this interval start and end that we're measuring the distance for part D? Starts at 3 and goes to 3 plus h. So if I'm thinking about the time interval 3 through 3 plus h and measuring how much distance I travel, this would be the description that we get based on what we were doing in number 2. So if you wanted to say this in words instead of during the interval 3 through 3 plus h, if you wanted to describe that more like a human might in English, it's still going to be kind of stilted because there's this mystery h in there. But this would be talking about a time interval from 3 seconds through a time h seconds later. So the distance traveled from time 3 through a time h seconds later, you could say, as opposed to time 3 through time 3 plus h, if you wanted to make it sound a slightly more like you're speaking. But that's the interval we're talking about. So the distance traveled, or the change in distance, from time 3 seconds to a time 8 seconds later. So 8 seconds later, then time t equals 3 is time t equals 3 plus h. All right, now what about part E? What's the beginning and end of this interval? The beginning is t, and the end is t plus 10. So this one we know the length of the interval. We just don't know where it is. How long is this interval in time? Yeah, it's 10 seconds. So it's an interval of 10 seconds that starts at mystery time t. So this would be a distance traveled then over a 10-second interval that starts at t. The last one was an h-second interval. Unknown length of the interval, it started at 3. This is an unknown beginning of the interval, but it lasts for 10 seconds. So make sure you can distinguish between those two. And again, it may help if you write out what's the interval. This is y final minus y initial. So inside the parentheses, x final minus x initial. If you want to just think in general, x is the independent, y is the dependent. But my initial time is t. Final time is t plus 10. So this one, I know that between those two, the change in time or the variation in time that occurred was 10 seconds, versus in the previous one, the variation was the amount that was unknown, h seconds. This one starts at 3 and goes forward h seconds, starts at t and goes forward 10 seconds. But otherwise, somewhat similar. I could talk about the change in distance. I'll word it this way this time. The change in distance over a 10-second period, and it's not any 10-second interval, unless this was traveling at a constant rate, in which case it wouldn't matter which 10-second interval, over a 10-second interval starting at time t, which is measured in seconds. So again, I'm just kind of abbreviating here, but these distances are all given in feet. The time measurements are all in seconds. All right, now looking at F, the numerator looks like stuff we were just talking about. Kind of like looking at part C. If this part F is to make any sense, there's a variety of things that could be. Like dividing by 0.5 is the same as multiplying by 2. But there's a reason it's written as division by 0.5 here. What does the numerator here mean? Kind of similar to the last one, right? Only, what's the difference between the numerator of F and problem E? Just, it's 0.5 second long interval instead of a 10-second long interval. And we've used the symbol X instead of the symbol T, but that part doesn't actually change too much about the meaning here. But I'd have this distance traveled, I'm just going to abbreviate this a lot, in 0.5 seconds, starting at X. So the top is a distance, and then I divide by this 0.5. Yeah, so I could say that this is double the distance traveled in 0.5 seconds, and then that would be a number of feet. Now, there says 0.5 seconds here. What if I decided that the denominator was 0.5 seconds? Because you can divide things, this distance in feet, you can divide things that don't have the same units. You just get different sorts of elements by the time you're done. If I divide this distance traveled in 0.5 seconds, a number of feet traveled in 0.5 seconds, by that time of 0.5 seconds, what sort of thing do I have? Yeah, I've got feet per second, so I've got a speed or an average rate over that half a second. So this could mean a lot of things. One of the quantities we're going to be talking about second half of the class is things like this, where if I measure how far was traveled in a small amount of time, this distance divided by time gives me an average speed for that time interval. And since this is half a second, well, it is a race car, so they can change speeds in half a second. If it was you driving on the highway over some random 0.5 second interval of time, your speed probably didn't change very much during that interval, so that'd likely just be what your speedometer said, only probably not in feet per second. But this could be some quantity that represents measured in feet per second, and it would be your feet per second during that half-second interval. So it would just giving you one number. I'll call it an average speed in feet per second. That's one thing it could be. It doesn't have to be, though. Like I said, dividing by 0.5 could be seen as the same as multiplying by 2, so this just could be double that distance that you traveled but during that 0.5 second long interval. It could represent that also. It's just thinking about why it might be written as division by 0.5 instead of times 2, instead of just to make math trickier. It could be because the 0.5 had a meaning that would make you think about the 0.5 seconds. Yeah.
So something like this is an exam, you pull out both answers.
Mm-hmm. Yep. Yeah, so this would, because it's obviously it could be either. It could be lots of things. There could be some other reason that we're dividing by 0.5 or multiplying by 2. But in any case, for it to make sense, this should be, well, when you're multiplying or dividing, if I divided by feet, I don't know what on earth that would mean. Feet divided by feet, I just get some number, a ratio of one number of feet to another. And I don't know why I might be dividing that, but that's something that we could do. If we divide by a different sort of unit, like an amount of time, distance divided by time, we can get some sort of speed or rate computation. But we could divide by other things as well. Addition and subtraction, just like with fractions, they have to be the same sort of items to be able to combine them. So if you're doing subtraction, you better have the same sort of units, or else doing that addition subtraction doesn't really have a meaning. But multiplication and division, just also like fractions, you can kind of do whatever you want. Doesn't matter if they're related or not. You'll just get stranger looking outputs by the time you're done. So keep that in mind. But let's talk a little bit more about functions and what they actually are. We've used all this function notation. All right, so, actually I didn't want to close that. I was trying to get it out of the way. All right, so this is where we left off on whatever day that was, Friday. So we talked about function notation and how to understand it, how to interpret it, how to write it, but not everything, not every relationship is a function. A function is a very specific type of relationship. Specifically, by calling something a function, we essentially, when we know what we start doing, we should know precisely how that's going to end up. Now, maybe it's a hard figuring out, maybe it's an easy figuring out, but consider making a phone call. And we want to think about how your phone functions. So what you get to choose, if you're going to make a phone call, is, well, what number do you dial? Okay. So that's the part you get to choose, do whatever you want. Sometimes it'll end it in this number doesn't exist or some sort of error messages. But if you're trying to call someone in specific, you hope that when you dial their phone number, you get them, correct? So you hope that, if your phone is working right, you dial a number and you get your mom, or you dial this number, you get Visa customer service, whoever it is. You hope that if you dial a number, you get the person that is listed as having that number. That is a functioning phone and phone service. So whatever number it is, I can dial a different number, get my friend, I can, whoever it is. And these, obviously, I could rearrange what order these are listed in, and all these arrows could cross. The arrows going straight across isn't the relevant part here. It's just that if I know what number I dialed, there's a specific person on the other end of the line that's supposed to pick up, or at least a certain business. Or maybe I'll get their voicemail. But I'm not going to, get mystery people. So for each value of the independent variable, Every time I make a choice on a phone number to dial, I get one specific person. Or for every value in general, not just phone calls, of an independent variable, the value of the dependent variable is determined. It's uniquely determined by the independent variable value chosen. So what if, just as some other variations on this, what if I dial this number and sometimes I get my mom and sometimes I get pizza delivery? Just depending on the whims of phone service, right? That wouldn't be what we want, correct? So this situation, not just with phone service and not just with your mom and pizza delivery, if one value of the independent variable can lead to one of two or more different results, although, maybe that's something that you want in certain cases, that's not really what you want with your phone, correct? You want your phone, you dial one number, you get one person. So you don't want to accidentally get your ex instead of your brother. That'd be an unpleasant day. But on the other hand, it's not necessarily bad. This situation, an independent variable leads to two or more dependent variable values. That's not what we want. But is it okay if your friend has two phone numbers? Like maybe, her, like either mom's landline and her cell phone. You could get a hold of her either way. Not a bad thing. Or Visa customer service probably has lots and lots and lots of numbers, depending on what credit card you're looking at the back. That's okay, right? It's okay to have more than one independent variable value chosen and end with the same result. What's not okay is the mystery. Well, I dialed this number, one thing's supposed to happen. So every time, in this situation, every time I dial that 555-1234, I get Visa customer service. It doesn't ever lead to my ex or whatever else. It's okay for two independent variable values to have the same associated dependent quantity value. It's not okay the other way around. So this is okay. So something like this, just mapping independent to dependent visual-wise here, that's okay. Like if I square -2 and I square +2, I get the exact same result. That's okay. The result of squaring something, that's an example of a math operation. That's a function. Every time I square a number, I get one specific result. I can square two numbers in lots of cases, everything except 0. I can square two different numbers and get the same result, but I can't take a number and square it, and sometimes I get one answer, sometimes I get another. That doesn't happen. The result of squaring, like y equals x squared, in that situation, x is an independent, y is the dependent, y is a function of that x. So each independent value needs to determine one dependent value, and only one, in order for the relationship to be declared a function. Now, not everything has to be a function in life. I'm just saying, if something is called a function, it has this specific quality. So let's take a look at data that we have, graphed data. So in this situation, one summer you and a friend visit a lake, measuring frogs and crickets and stuff. And that sounds like a really weird thing, but I had a roommate in college who was a natural resources major, and she had a summer job laying on a hill and counting the different numbers of species of birds that were flying over. There's a lot of weird jobs out there. So this could be somebody's summer hobby, measuring frog and cricket chirping. There's probably lots of scientific things you want. Maybe something could tell you about the environment. So number of ribbits in 1 minute. Maybe this tells me if there's global warming or not. Well, let's see how this relationship goes. Or other friend measuring cricket chirps. Measuring chirps in 1 minute and comparing that to the temperature, seeing if that defines a relationship that we'd call a function. So both of these are perfectly fine, things we can graph. There's a relationship between them of some sort. It's just, does it define a function or not? Does knowing about the independent quantity tell me something specific about the dependent quantity? And maybe looking at this, you already know these results, but just keep in mind, graphs can be shown in a variety of ways. And what we're going to consider here is suppose that the number of ribbits or chirps in 1 minute is the independent quantity. Is the other actually dependent on the first? Is the temperature dependent on these chirps and the chirps and ribbits. So if I say that the independent is these 2, 3, 4, and 5 ribbits per minute for the frogs, then the dependent quantity would be the temperature. And when there's 2 ribbits per minute, the only data that I had, now this is just collected data. We could need to collect more to prove something. But based on what we have already, after 3 ribbits per minute, we've got that happened at 2 different temperatures, maybe one in the afternoon, one late at night when it was cooler. Same with 4 and 5. There are lots of different temperatures corresponding to the same, what we declare this independent quantity of number of ribbits. So does this relationship, does this represent a function where this independent quantity uniquely determines a dependent quantity? No. By knowing that there were 3 ribbits in the minute, or 3 ribbits in a minute, you would not know what temperature it is, for sure. It's like dialing one phone number. You don't know who you're going to get for sure. So we picked the thing on the left, picked the number of ribbits. Does that tell me what temperature it is? No, might be warm, might be cold, might be a whole bunch of different temperatures. So this one is not something where the temperature is a function of the number of ribbits per minute. That's not true in this case, because the temperature is not uniquely determined by how many frog croaks we hear. So crickets, on the other hand, now again, this is just collected data. Maybe if I collected more data, it would be, wouldn't match up so well. Maybe it'd look more like the frog graph. I'd have lots of different temperatures. But from what I have right here, if I declare this number of cricket chirps per minute, which it's a lot more than frog croaks, you'd have to have very good ears for this. I would assume a recording and then slowing it down to count things, or having the computer count. But for each of these, and there's a lot more different values here, for each of these different values of chirps per minute, 92 chirps per minute in this graph is right here. It corresponds to just one temperature, looks like a little bit less than 60 degrees. And there's no other instances of 92 chirps per minute. So there's no other temperatures it corresponds to. Meaning, and same with all of these, at each individual temperature, there's specifically one, or at each number of chirps, there's specifically one temperature that corresponds with that. And this is actually something that that scientists have decided, that crickets chirp at a faster and faster rate based on the temperature. It isn't just, I didn't make this up. Well, kind of did, but this is actually kind of what happens. If you were to collect more and more data, the more chirps indicates higher temperature, and likewise you could actually say the higher the temperature, the more chirps you should expect. Which, when you can go back and forth like that, this is extra information. If either way, one determines the other and the other determines the first, that's called a one-to-one function. Means every independent variable corresponds to precisely one dependent variable, and what you were calling dependent could have been the independent of a function set up the other way around. Every dependent variable corresponds to precisely one independent variable value. Sorry, I left out the word value in that. But in any case, all we need for this to be a function is whatever we're declaring the independent variable to be, to correspond to, at most, one dependent variable value. So each dependent variable is uniquely determined by an independent variable value. So the second one, the temperature is a function of noises that the crickets were making. So just to summarize, one unique value of the dependent variable corresponds to each value of the independent variable, means that we've got a relationship that is a function, reliable function, actual function, whatever. You're trying to figure out if something's a function. Sometimes you get the no, like the data graphed on the left there. Because if I thought that this ribbits was independent, that the number of ribbits would tell me the temperature, I would find out by this graph, no, that's not true. Knowing the number of ribbits does not tell me the temperature. It could be a whole variety of temperatures. So that's not a function with ribbits as an independent variable. All right, so what I want to do here is take a little bit of we saw some problems earlier with same context, but I want to talk about constant rate of change and mix in our function notation, just as a little kind of blend this all together. So, give you a second to read this story, but I'll read it along. You're pulling a drain plug from a sink you're washing dishes in. It's partly clogged, so it's draining extremely slowly, however at a constant rate. You didn't throw in any Drano to assist the process. So suppose that W of T represents the height of the water in the sink, measured in centimeters, at T minutes after you pull the drain plug. And the height's decreasing at a constant rate of just over 1 centimeter per minute. So imagine a really deep sink so that this doesn't run out of water in a minute. But every minute, this is decreasing at, it's decreasing at a constant rate. Every minute it would decrease by 1.23 centimeters. But that's the not very good description of how this constant rate works. The height's decreasing by 1.23 centimeters per minute. How could I say that more generally than in a minute it dropped by 1.23 centimeters? Anyone have a description for how to state that rate a little bit more generally? All right, go ahead.
For every change in time, the sink drains at a rate of 1.23 centimeters per minute.
All right, for every change in time. So how are we measuring the time?
In minutes.
Okay, so any amount of time in minutes. What do I do to get the change in the
It's multiplied
depth?
by a rate of 1.23
Right.
centimeters per minute.
Right, multiplied by 1.23 centimeters per minute, and that change that I get is then going to be measured in centimeters. Right. So for any amount of time that passes measured in minutes, that number times 1.23 tells me the amount of change in the height. Is the height of the water going up or down? Down. So you might even want to say something like times 1.23, that's the amount that it decreases, or you could use a negative in there if you're thinking, more thinking computations. I'm going to, times negative 1.23 tells me the change in the height of the sink water, not the sink, measured in centimeters. But yeah, for any increment of time measured in minutes, take that number times 1.23. That number is how many centimeters lower the water is going to be in your sink after that amount of time. All right, so just keep in mind it's not just after 1 minute, it drops by 1.23, or after 2, it's 2.46. After any number of minutes, multiply by 1.23, that's the decrease in the height, or after any number of minutes, or during any interval of minutes, the length of however many minutes that is, multiply by negative 1.23, and that's the change in the height of the water in the sink. So, there we go. So thinking about what we were doing earlier with the race car, and thinking about how we did this last week, two different ways that you might be able to express the variation in the height of the water in the sink between time 2 and time 6 minutes. So think about one way that you could write that with function notation like we were doing earlier today. And also, we've got a constant rate here. You might be able to express a computation and actually know the answer to how much did the water drop. So take a minute or two. We have more information here than the race car problem. This is going to jump out on me. Come on. There we go. So what's one way that looks like the same way we did with the race car, the with function notation? What could I write to express the change in height of the water or the variation in the height of the water during the interval time 2 through time 6? Oop. Let's see. Got fat writing again. So close this out. W6 minus W of 2. Y final minus Y initial. So in terms of, to find change, just like I think the second day of class, it was Z. We were talking about gigabytes of memory on your phone and so forth. Final minus initial will do the trick. And this is a way to express the final height, or the height in the water in the sink at 6 minutes. And this is the height initially at 2 minutes. The interval we're talking about was 2 through 6. Now, W of 4 would be the same value in this case, but W of 4 means the height of the water in the sink at 4 minutes or something. So let's, instead of that, actually it might or might, no, it wouldn't be the same thing here because we're not starting at height 0.
What is it constant?
It is constant, but the height of the water, I don't even know what the height started at. So I don't know, maybe it was 1,000,000 centimeters at time 0. So by time 4, it's a lot. Whereas during this 4-second interval, how much did the height of the water change? Yeah, it changed by 4 seconds. We have 4 seconds worth of dropping by 1.23 centimeters per minute. Here, let me write this in the other order, actually. So for any amount of change in time, for any passing time, the height drops by 1.23 times that amount of time measured in minutes. So this gives me a number of centimeters that the height would decrease by, the negative there, in 4 minutes. This is our MDX sort of way to write this. So dy equals MDX. I can say dy to find a change in a y variable. I can do final minus initial. But if that, and this is something we talked about back a while ago before function notation, if y depends on some other variable x, if x and y are in a relationship together, then I can also determine y by measuring changes in x. And if we've got a constant rate of change relationship, here's what we've got. So I've got a constant rate of change between x and y, then a small amount of change in x determines a specific amount of change in y. It's proportional to it, just multiplying by the change per minute. 4 minutes at 1.23 centimeters decrease per minute gives me, I don't know, 5-ish. Let's see, negative 4.92. Centimeters. I can actually compute how much it changes because I know specifically at what rate it's dropping all the time. I know the amount of time that it dropped for, and I know the rate of dropping water height. So because I have function notation and I have a constant rate of change, I have 2 different ways I could express this same amount. All right, final minus initial or MDX. And the dx, there's 4. This was 6 minus 2, right? This didn't just come out of thin air. This is x final minus x initial. All right, so I'm going to ask you a few other questions with this. Same sort of idea, see if you can express these in other ways. And we're going to continue with this tomorrow, but just to give you an idea, here, let me clear this off. I'm going to post this tonight as a part of your assignments. But just to do this part, well, A subpart. Suppose that the height at time 2 was 8, meaning at time 2 seconds after you pulled the drain plug, the height of the water was 8 centimeters. If I wanted to find this height of the water in the sink by time 6, then, well, we just figured out from up here that I could do, W of 6, or W of 6 minus W of 2 to get the change in the height. Now, if I try to express W of 6 by saying, oh, well, it's whatever it was at W of 2, that's 8. And then I could do it like that with function notation, or I could say, well, W of 6, that's the height by the end. It started out at 8, and then I subtracted whatever we just had, 4.92, which was 4 times 1.23. So I can actually compute the height at times 6, because I know that's 4 seconds later at this constant rate of change. So we could do this with function notation, but just try to write a computation. There's that. If we actually did the computation, 8 minus 4.92 is going to be what? 3.08? No. Yeah. So in any case, I'm going to have a series of questions. We'll go through them tomorrow. Or not tomorrow, Wednesday. But also, after we do that on Wednesday, we're going to be talking about GC stuff, graphing some curves and line segments and restricting domains and making sliding points and all sorts of fun stuff with function notation. By the way, before you run out, to let you know, there is a Canvas quiz. You might, if you were on Canvas today, you probably already saw that it's there. It's available as of like now or a minute ago. Do not, as you found out, do not try to start it and then close it and then come back an hour later. It's only a 10-minute quiz. It doesn't know that you've closed your computer. Once your 10 minutes start, they start.